Good afternoon, everyone. This is Arun Sharma calling from Midas, conducting the session today. I welcome you all to the session 6th of our online course at Midas Elite Center. The topic of session today is advantages of utilizing numerical modeling methods for retaining wall design. And Midas holds the copyright to the material that we are sharing today, so don't share the material outside this platform without our consent. At the end of the course, participants will be able to understand a comparison between the retaining wall design methods. They will be able to understand the reinforced retaining wall design and analysis method and how to consider various conditions in retaining wall analysis. So the session today is divided into 4 chapters. First, we'll be talking about some background information about different types of retaining walls that are there, what methods are there for retaining wall analysis, and what role numerical analysis has to play. Additionally, in the second chapter, we'll be talking about different approaches for retaining wall design, and then we'll have chapter 3 where we'll be talking about how to use numerical analysis for doing the retaining wall analysis. In this chapter, pay special attention to what exactly is soil structure interaction and how we can consider it. And finally, we'll have chapter 4 where we'll be discussing a case study about a project that has a very long, I should say, very long circular retaining wall around the periphery of our excavation site, and that particular retaining wall called for 2D as well as 3D analysis. So we'll see what conditions led to that decision from the engineers. In between chapter 1 and chapter 2, and between chapter 2 and chapter 3, and between chapter 3 and chapter 4, we'll have 3 quizzes of 5-minute duration with 3 questions, multiple choice questions, and do read the instructions carefully before answering them. So this is chapter 1 where we'll be discussing about retaining wall background. So as you can see in this slide here, on the left side we have the gravity wall, which is primarily used for sustaining different types of slopes with different applications. So this is called retaining wall because this is called gravity wall because they have their interiors either filled with gravel or soil, and they are massive structures. They are self-stabilized systems, and they are used at locations where they have no limitations, no space limitations. But as you can see, they are not very aesthetic in appearance and have a crude finish. On the right hand side we have MEC walls, which is also a type of gravity wall, but here you can see it has such a clean finish or neat finish. So where you want to have where you have to use a gravity wall, but it is used in a commercial place and it affects the aesthetic environment of the place, you generally go for MEC walls over the conventional gravity wall. Then we have a semi-gravity wall, and in semi-gravity wall you can see that it has an inclined surface, a sloping surface behind it, so it gives this wall a leaner appearance as compared to the fully gravity wall. But this additional sloping surface that is at the other side or behind the this main wall gives the structure additional stiffness and strength against the overturning, and it makes it more stable. Again, it has a combination. It could either have a core filled with gravel or filled with concrete, or it can also be constructed as a monolithic set, something like a buttress wall. Then on the right hand side we have cantilevered wall. Now this type of wall, as you can see, is very sleek, and this is a completely reinforced concrete wall, as you can see here, and this is useful where we have tight spots, like space limitation is concerned. So there we use a fully reinforced concrete cantilevered wall. As you can see, it is just standing on the uh, uh, the the heel and toe arrangement, and it is like a cantilever, and this the name cantilevered wall. So these were the most common type of retaining walls. Now when designing these retaining walls, we need to perform a set of checks. Now this is a very standard procedure, and I'm sure everyone in this room would be familiar with that. So I'll quickly go over the stability checks. So first of all, we have this sliding stability check, which is the formula is pretty simple and straightforward. Driving horizontal forces divided by the resisting horizontal forces will give you the factor of safety. And if the factor of safety is greater than 1.5 or higher, then it is considered to be safe. Then we have overturning check. Now again, the formula for overturning check is again pretty simple and straightforward. So resisting overturning moments, if they are divided by the driving overturning moments, if this ratio is greater than 1.5 or more, we consider the wall to be stable. Then we have a bearing capacity check. Now if you are dealing with soil strata that are where there are excessive volume changes, or it can consolidate further, or there is not proper access to drainage, so at those locations you can expect the some kind of settlement occurring under the foundation of the wall. But again, there are empirical formulas to deal with these kinds of situations, and if your bearing capacity factor of safety is not greater than 3, then you need to take some settlement controls. But most of the time with your empirical formulas you can assess these 3 checks. But there is a fourth check where you cannot really predict the behavior through empirical formula, which is called the overall stability. What if the entire slope or the hillside scoops out the entire soil layer? Then there is all the stability checks that you have applied for sliding, overturning, or bearing capacity are no good if the entire slope is unstable and slides out. And therefore there doesn't exist an empirical formula to determine this, and for this type of situations we have to perform a numerical analysis to assess that how the slope would deform, or would it be stable by itself, or what will be the failure surface if such type of failure occurs. And if that failure occurs, then you can take precautionary measurements well in advance. So basically this overall stability check, or also known as global failure check, can be done only through a numerical analysis method. So let's talk about how numerical analysis help you out for slope stability or overall stability check. So the first and foremost method, which is very common and very popular, that everyone is familiar with, is the limit equilibrium method. As we studied in our schools, the slope is divided into fine fragments or wedges, as you can see. So they are like rectangular strips, and we define a grid set which has a different radii but passing through a given point, and then the program or whatever software you use would consider all the permutation and combinations to check whether which of the given radii has the minimum factor of safety or will be the first one to fail. So we have to define this grid in advance. So what we are doing is basically we are defining a set of failure planes in advance and then checking what will be the factor of safety at different surfaces or different radii. So this method no doubt is the most popular method, but you need to define failure surfaces before analysis, and therefore engineers have to do trial and error to search optimum factor of safety. And the another limitation for this type of method is it usually is considered only circular failure surfaces. So this brought the need of an advanced method of analysis known as Shear Strength Reduction Method, also known as SRM. So in this method, what we do is we create a finite element model for the slope or the soil, the backfill, the retaining structure, and if there is a retention system or reinforcement. And then the software or your program would continue to do the analysis by reducing the shear strength of all the layers in the subsequent manner. And as it proceeds with lowering the shear strength value or reduces the shear strength, it hits a point where the entire slope is mobilized, and at that point it clearly shows that the maximum deformation would occur at this particular layer at this particular force, and therefore you can easily assess when the failure will occur and what will be the failure plane. So and most importantly, here you are not assuming anything. Here you are not assuming a grid size or doing any kind of permutation and combination. Here the soil is behaving accurately as per the constitutive material model that you have assigned. So it is more natural or more accurate way of analyzing a given situation. So basically this slope stability analysis method is based on FEM or finite element method. There is no need to define failure surface before analysis, and it generates failure surface as per realistic behavior. Hence non-circular surfaces can also be obtained, whereas here you mostly go for circular surfaces. Here this could be any irregular surface based on the shear strength reduction method. Then let's see what are the main components in the modeling of a numerical analysis model. So the first and foremost part is the ground itself. As you can see, the yellow colored mesh set is ground. So for modeling, for 2D analysis, which is the most common analysis method, we use plane strain elements for representing the ground condition. Then we assign constitutive model so that the soil can behave as per the real soil behavior, and there is no need to input any earth pressure. If you remember from our previous lectures where we talked about slope stability analysis and retention systems, we often talked about the conventional method where you apply the earth pressure onto the structure based on active earth pressure and earth pressure at rest, and then determine the structural forces in the members for designing. But here, if you are dealing with a numerical analysis model, you need not pre-calculate and apply the earth pressure onto the system, because here you are using the constitutive models, you are using the realistic forces, so these earth pressures are automatically computed and applied to the structural system here. And there is no limitation on the angle of the backfill, so it can be at any angle you want depending upon your slope and depending upon the location of your retaining wall. So you have more options, or you are more flexible with handling different types of backfills at different angles. Then the second most important component is the wall structure itself. So modeling for modeling the wall structure, now depending upon what type of wall you are dealing with, if it is a gravity wall, then we would model it as 2D finite elements using plane strain members. If it is let's say a cantilever wall, or let's say MEC wall, then you can model it as a single beam element also. Then you define the stiffness parameters for these elements that compose the wall members. So if it is a plate member, then you have to define the stiffness parameters by choosing appropriate concrete material properties. If it is beam member, then you have to define the actual cross-sectional sizes that is representative of that wall. And then you have to consider soil structure interaction using interface elements. Now, what is soil structure interaction and what is interface element is I'll discuss in detail in third part of this session. But for now, you can just understand it as something like a coating applied on the periphery of retaining wall which is in contact with soil. So basically, this is your structure, this is your soil, and how the soil will interact with the structure is governed by this dark blue line, which is the interface elements. Then we have reinforced structures. If it's a reinforced retaining wall, then you would have different types of reinforced retention systems that would be useful. So you can choose based on the element types that are available and what purpose they have to serve. So if it is a bonded or unbonded anchor, it's a rock nail or soil nail. So depending upon what type of retention system you have, you could choose either truss members or embedded truss members. And if it is a 3D analysis model, then you can also apply it using plate elements. So right now you can see this is just a 2D representation, and here you will see this is a single line element for reinforcement. But let's say this model was not 2D and it was 3D, so it will have a third dimension in that direction. So this 1D member will then span in 2 dimensions, and therefore this will no longer be a 1D member, it will be represented by a plate member. Then what is the advantage of having numerical analysis? So first and foremost, advantage of having numerical analysis in terms of determining the stress and deformation that is occurring not only in the structural system but also in the soil. And some engineers have this misconception that okay, we are doing finite element analysis, so we'll get all the bearing capacities directly. So it's not the case. Finite element analysis does not give bearing capacity directly. What it does is it helps you to simulate construction stage analysis. It gives you displacement and stress results. So here you can see the displacement results of a segmentally constructed retaining wall with reinforcements, and you can see the red zone is right here instead of being somewhere here where you would expect maximum deformation otherwise. And this can be used to obtain forces or stress from the structures. So basically, through numerical analysis, you can obtain accurate design forces. You can find out what is the structural force in this particular member and then design it accordingly. And it gives the forces not only for your wall elements but also for the reinforcements. So you can see the forces are obtained in the axial forces are obtained for these reinforcements. Now if you notice here, the axial forces are higher at the bottom as compared to the top. This is because we started erecting the structure from bottom to the top. So we had as and when we started putting in the backfill, the lower part of the structure would start deforming, and that is why we have the retention system or reinforcements. So they will hold it in its place. So that leads to excess or higher axial force in the bottom part. And the results that are thus obtained, engineers can compare them with the design code to check for the maximum values. So let's say the rebars or the reinforcement system that you are using has a certain limit or capacity. Now you can check with these results whether the capacity is exceeded or not, and if it's not, then you can either choose another or alternate size of the rebar or the anchor bolt in order to optimize your design. So in this manner, finite element analysis is helpful in giving you an optimal design for your retaining wall system. So this brings us to the end of chapter 1. So let's quickly go over what we learned today. The overall stability check needs numerical analysis, while overturning, sliding, bearing stability checks can be performed using empirical formula. Engineers need factor of safety for slope stability that determines the overall stability. LEM, or also known as limit equilibrium method, is the most popular method but calls for trial and error. Strength reduction method, or SRM, is a finite element method based method for slope stability analysis. SRM saves trial and error and generates failure surface that might not be circular. Numerical model consists 3 components: ground, wall structure, and reinforcement. Numerical model gives stress and deformation results considering construction sequence in soil, wall, and reinforcement members. And finally, numerical analysis doesn't give bearing capacity directly. Instead, it gives optimal design forces for wall and reinforcement members. So now I'll initiate our quiz number 1, where you'll have 3 questions, 5-minute duration. Do read the questions carefully before answering, because we'll have different types of questions. Either pick one or pick all that apply. So do read them carefully. So let's move on to chapter 2. We will be talking about the approaches for retaining wall analysis, and there are different approaches based on different wall types, and also we will cover seismic analysis here. So as you can see, for gravity type of retaining wall, there is something called a stabilized zone. Now this is called a stabilized zone because this is basically backfill of for the retaining wall. So we can control this material property. We can we can consolidate it if you want. So this is something that we can control, or and whereas outside this stabilized zone exists the natural soil, and this behavior is not really under our governance. So what we do is we must uh, carefully examine the soil properties of backfill as well as the soil in outside the stabilized zone to determine what constitutive material model best determines or gives the behavior of these two different types of zones. And if since we're dealing with gravity walls here, they are massive concrete structures in itself, and they have a huge big filling inside them. So they're self-stabilized structure, like I said before. And when you are dealing with the most conventional type of gravity walls, then the conventional approaches that we just learned, that is uh, the checks that we talked about, the sliding, the overturning, the bearing capacity checks, all that can be used to design the gravity types of wall. So basically, for a conventional simple wall, normal design will be enough. And this is what we have been doing all this time. Whenever we come across a retaining wall, we start with these simple design procedures and extract what should be the design forces onto the members and just to the design. But when engineers are dealing with the MEC wall, it is required to perform numerical analysis. And the important things that you should consider in that is that stabilized zone that I just talked about uses a different material property or parameter from the remaining soil, and sometimes they are reinforced structures, so you should model them or and consider them using the structural elements. So since MEC wall in itself is constructed as different modules put together in stacks, so basically it is a segmentally constructed structure, so you must consider its actual construction procedure, and at the same time you must use proper element types in order to generate or simulate the same behavior. So just briefly going over what I just said, for stabilized zone use appropriate material parameters which are different from the soil strata, and for reinforced structures, that is the retention system like tiebacks, anchors or soil nails, use proper structural elements to simulate it. And sometimes the reinforcements are also applied at different spacing along the longitudinal length of the structure. So like I said in the previous slide, where we were just talking about just one 2D cross section, and said that let's say it has a third dimension, then we need to do a 3D analysis. Now what determines or distinguishes between a 2D analysis and 3D analysis is actually the spacing or the arrangement of the reinforced or the reinforced members or the reinforcement members. So if the arrangement of the reinforcement widely varies from one section to another, or if you are using a reinforcement member which behaves like a geotextile or a grade form or has a two-dimensional properties, then you should go for 3D analysis. Now most of the times these reinforcement patterns or layouts are pretty symmetric and regular, so we need not perform 3D analysis on a regular basis. But but it is always good to know that if you encounter this kind of situation where you have uh, reinforcement arrangements which are differing from one section to another in the third dimension, then you have to perform three-dimensional analysis. Then let's see how we design cantilever wall or anchored walls. So as we know, cantilevered wall is like just standing simple cantilever here. You have earth on both sides, and you have some surcharge, and cantilevered wall, if you look at it, it just has one particular structural member, and that is what we have to design. So basically it is this wall member that governs the design, and our entire focus of the design is on this wall behavior. So when we do a numerical analysis, we must consider how this wall was constructed. Sometimes when you are dealing with tall walls, they are not constructed in one shot, so they are constructed in increments or segments. So you must perform the numerical analysis to check the behavior of the wall based on its construction stages, and pay special attention to the interaction of the wall and the soil. So if you see this brown surface that we have highlighted here and placed in this box, is actually the interface between, or interface material between, the wall and the soil. And since we have to monitor the behavior of the wall, because that is what restraining or resisting the earth pressure and keeping the entire slope or the soil strata behind it in place. We have to monitor as how this wall would interact with the soil layer. So therefore we have something called interface members. Now I know this could be a new concept to engineers in this room. So what I'll do is take up this particular topic in detail in our chapter 3, which is the subsequent chapter. Then when you're designing the anchor type of wall, then it is largely the anchor bolts that are taking the bulk of the force and stabilizing the structure. So and as you can make out that if our cantilevered wall is not sufficient, maybe in section limitations are there, maybe the size limitations are there, maybe the depth limitations are there. So when the wall alone is insufficient to sustain the loading, then we have to go with some kind of back end support, which is like a tie back or an anchor bolt like this. And whenever we are dealing with these types of bolts or anchors, they could either be bonded, like bonded just at the end or throughout, like a soil nail, or it could be unbonded, like there is no grouting whatsoever and they are just drilled through it. So depending upon what type of retention system you are using, you should model that accordingly. But from this slide I want you to understand that for anchored wall type, the prime focus is not on the wall alone, it is on the retention system that you are using. And therefore numerical analysis is needed to check the stress and the deformation in these retention system. And like I mentioned before and I'm mentioning again, based on the site conditions you might need to perform 3D analysis. So in the case study that we will be talking about, that is a good example where you would actually need a 3D analysis over 2D in order to determine these results. Then let's move on to the seismic analysis itself. So you can see there are different ways of performing seismic analysis, and I'll walk you through this tree real quick. So first we have pseudo-static analysis, then we have something called pseudo dynamic analysis, and then we have something called numerical analysis. So what is pseudo-static, what is pseudo dynamic, and what is numerical analysis, I'll discuss in detail. But for now, you can just understand that pseudostatic is a set of formulation which considers the mass of the structure to be at rest and not in any in dynamic state. So it just considers the mass of the structure at rest, which would cause a certain amount of horizontal or vertical force onto the structure when excited under earthquake. Then we have pseudo dynamic, which is purely a dynamic analysis, and again it is a collection of empirical formulas that have been formulated based on different theories over the time and refined over the period of several years to generate some kind of formulation to represent the dynamic effects. Then we have a numerical analysis, which is primarily based on finite element analysis, and under numerical analysis you can see there are two divisions. One is equivalent method and other is time history method. Under equivalent method there is 1D equivalent method and 2D equivalent method, whereas under time history there are two branches, linear time history and non-linear time history. Now if you notice in this presentation, in this slide, pseudo-dynamic and non-linear time history are not bold, whereas all other types I have used bold letters. Now the reason I've done this is that pseudo-dynamic and non-linear time history analysis are rarely used, and I would say pseudo-dynamic is rarely used because I haven't seen any engineer applying pseudo-dynamic analysis. I have seen cases where non-linear time history analysis is needed in very high seismic zones, but pseudo-dynamic analysis is hardly used. So let's go into a little more detail about what are these methods and their formulation. So in pseudostatic analysis, as you can see, it has a combination of, it basically computes the weight by gravity times acceleration in the horizontal direction. So this is basically the force by acceleration. So it is actually the mass that you are considering that is acting onto the wall depending upon the angle of the face. So what we do is we first take the actual shape of the gravity wall, then we connect the dot at a given angle depending upon the internal angle of friction, and then we say that okay, this is the wedge that will fail. So what is the mass of this wedge, and that would cause instability in the lateral direction and in the vertical direction. So we compute this FH and FV from this method. Now there are different theories that have been refined over the period of time, and every time a new theory comes up, it has something or the other to modify with different coefficients, but the basic skeletal remains the same. And then now let's talk about pseudo-dynamic analysis. This approach monitors the dynamic characteristic of the seismic loading, and for this, if you would like to read more, you can read Steedman and Zeng's method or Chaudhary and Nilambkar method. Now like I mentioned before, this method is not is hardly used, and to be honest with you, I have not seen engineers using pseudo-dynamic analysis at all. Wherever they need seismic analysis, if it's a low seismic zone and they want to just do some quick and easy checks, they go for pseudo-static analysis. And if they have to consider dynamic analysis, and or if they have access to a numerical analysis, then for seismic analysis they mostly go for numerical analysis. So here in this presentation, I've taken out all the formulas and computation for this pseudo-dynamic analysis, but if you would like to read more, you can follow these two methods and read about it. So in a nutshell, engineers prefer either pseudostatic analysis or numerical analysis. So let's talk about numerical analysis and how it is applicable. So like I said, there are two main branches. First is equivalent linear analysis, and in equivalent linear analysis we have two division, 1D and 2D. So basically 1D equivalent linear analysis has no structural member in it, and I'm sure many of you must have already used or applied this method for seismic zones. So what we do here is that we just use an equivalent linear analysis method to determine what would be the ground motion from the project site. So since there is no structural member involved, so we cannot really capture the response of the structure, but just get the ground motion. Whereas in 2D equivalent linear analysis, you can actually model or consider the structural component of the component, and from there you can simulate soil structure interaction as well. So if equivalent linear analysis was there, then why did engineer feel the need for time history analysis? So basically time history analysis is useful for determining the dynamic response of the structure. So linear analysis, as the name suggests, is linear and it doesn't take into account the dynamic effects. It is just taking into account something like, you can consider it to be similar to pseudo-static analysis, something on those lines. If you really want to draw an analogy. But time history analysis, as you can see, has two branches, linear and nonlinear, and linear analysis is useful for determining the dynamic response due to seismic loading. So what we basically do is that we have this ground motion or time history graph, and you make this numerical model where you have the structural component, you have the soil component, and then you apply this ground motion to the structure to obtain how the structure would actually respond to this kind of earthquake shaking. What linear time history analysis is not able to capture is the estimation of permanent deformation, where we have to consider nonlinear time history. So when we say nonlinear time history, we are actually talking about the nonlinear behavior of the soil layer under the earthquake excitation. And when you do that, then you can see after the earthquake has been done, is over, what is the permanent settlement or permanent deformation in the soil strata, what was the response of the structure to that earthquake. But again, this type of nonlinear time history analysis, which will give you the dynamic response as well as permanent deformation, is not very often used, and it should be used only when it is a very critical project or is in a very high seismic zones. Then only this method is used. Otherwise, majority of the time you would be using linear time history analysis. So this brings us to the end of chapter 2, and let's quickly go over what we learned here. So the analysis approach is based on the wall type being designed. So there is no a set pattern that all walls should be designed based on this. Now depending upon what wall you are designing, you would have to perform a separate type of analysis and determine the results. So basically for conventional gravity walls, you can design as per the empirical formula method that we have been learning and using in school. For MEC wall, we need numerical analysis for the estimation of deformation and stresses during construction. In cantilevered wall, focus is on wall behavior, thus numerical analysis is needed to consider soil structure interaction. And in anchored wall, the focus is on the retention system, and thus numerical analysis is needed to consider stress and deformation in the retention system. Pseudo-static analysis and numerical analysis are preferred for seismic analysis of retaining walls. Equivalent linear analysis and time history analysis are two types of numerical analysis for seismic analysis. Equivalent linear in one dimension is used to obtain ground motion, and in two dimensions or 2D is used for soil structure interaction. While time history in linear gives dynamic response to seismic load, and nonlinear is used where permanent deformation assessment is needed. So basically, nonlinear time history analysis is the ultimate thing that you could do for a retaining wall and high seismic zone. But most of the time we do linear time history to determine the dynamic response of the structure due to the seismic load. Thus, nonlinear time history is useful in high seismic zones. So I hope that explanation was clear enough, and it's time for quiz number 2. Similar to the previous quiz, you will have 3 questions and 5 minutes. Chapter 3, How to Use Numerical Analysis. So friends, in this session we'll be talking about things that are needed to be considered in numerical analysis, and what is soil structure interaction and how to consider it. So first of all, whenever we are creating a model in numerical analysis or on any platform, then you have to determine the boundary effect, and for this there are thumb rules that you need to bear in mind whenever generating these models. Now these thumb rules are determined based on several model files and several field tests. And if you notice here, then you'll see the height. If the height of the wall is h, then you would have to consider the extent of soil as 3 times the height of the wall. And if you see if the length of the foundation is L, then you have to go below the foundation to approximately 6 times the length of the foundation. And in the same manner, you have to consider in the front side 2 to 3 times of the height of the wall. So if you add these two up, you will see that if h is your height of the wall, then you have to approximately consider the boundary in the horizontal direction as 6 times the height, and if the width of your foundation is L, then you have to go below the foundation to approximately 6 times the length or the width of the foundation. So these are some empirical formulations that you should bear in mind. Now, why were these empirical formulations or these boundaries were defined? The reason for this definition is that whenever you are considering a finite element model, then the stresses need to be dissipated in the neighboring soil strata. Now, to what extent would you like to see them dissipated? That is what determines these boundary effects. So let's say there is an adjacent structure here. You would like to see whether the stresses from this whatever construction or whatever structure you have here, how will the stresses due to this construction would affect or dissipate and affect the adjacent structure. So usually in this, anything within this boundary frame would be affected by this structure. If you see when you are looking at the results, if you see the stresses are not zero at these ends, but rather they have some significant value, and you can see through contour plots, you would have to take a bigger boundary until a point you reach a boundary where you don't have any more stresses at these at the outermost boundaries of the soil strata. So just to summarize, this boundary effects is needed so that the stresses are fully dissipated in the neighboring soil strata, and beyond that you can determine that there's no additional stress coming because of this existing construction. So that is first and foremost. Now the second most important thing is the material behavior. As I pointed out earlier, then that there are different type of different components of a numerical model. There's a soil layer, there is something called backfill, there is a foundation, then the retaining wall itself, which could either be a wall or constructed in different blocks, and then there is reinforcement or the retention system. So first of all, let's start with soil parameters. So for soil parameters, you need to pick up the appropriate constitutive model. Most commonly used one is Mohr Coulomb, and similarly for backfill parameters, you can choose the constitutive material model as Mohr Coulomb. Now since the two soil types might be different, but they are still behaving as per Mohr Coulomb, their parameters could be different. So separate field tests should be performed for backfill material and soil material, and use those appropriate parameters for definition of these models. So this is very important. Then the material properties for wall and foundation. Most of the time we deal with concrete structures, so we can use concrete material models or steel material models. Now for geotechnical analysis, and especially for the analysis of retaining wall, we assume that the structural system never yields. It is within its elastic range. So therefore we design it in such a manner that the structure is never yielding or going into a plastic or inelastic zone. So it is safe to assume that your concrete behavior is elastic and steel behavior is also elastic. And then you can use different types of reinforcement depending upon what type of model you are working on. Is it a 2D analysis or 3D analysis? And you can pick from different types of reinforcement options available, like geotextile, anchor, soil nails, and blocks. Then I've been talking about this thing for last half an hour, that construction stage analysis is very important for numerical analysis. Now I'll tell you how to simulate this construction stage analysis and what points should be kept in mind. Basically, when you are constructing a retaining wall in a sequential format, you should always start as your first stage as initialization stage. This means that the field is or the slope is existing as it is in the field, and it is stabilized or fully consolidated under its own self weight. So you'll just model the existing soil strata in whatever state it is, and set the displacement after this stage as 0. So this means that whatever has happened prior to our construction is our initial condition now, and whatever happens thereafter is something we'll monitor. So then we start with the excavation of the foundation. So we have defined different mesh sets that we can deactivate to create this excavation pit for our foundation. Now once we have excavated, we'll obviously place the foundation. So you'll pour the concrete. So initially you started with the soil material for this mesh set. Now you will have the same mesh set, but change the material from from soil to concrete. And then you'll start erecting the MSE wall if it is constructed, or any kind of wall if it is constructed in segments. So you can see a tiny block placed here. Then you'll pour the backfill up to the height of the segment. So you'll have this backfill material placed, and then you'll apply the reinforcement on top of this backfill to hold the next segment in place. So you'll have this kind of reinforcement laid down. And then we'll keep on repeating the step. That is, we'll first have the segment block placed, then we'll pour the backfill, then we'll apply the reinforcement, and then move forward. So we'll continue doing this till we reach to the desired height of the structure. Now sometimes you would need multiple model files depending upon what platform you're using to generate or analyze these conditions, but a good program will be able to simulate a construction stage analysis in one platform, so that you don't have to make 1, 2, 3, 4, 5, 6 and then n number of model files to analyze each stage independently. Just for your information, this particular model example that I'm sharing with you has 81 construction stages, because the wall was constructed in different blocks. So the number of construction stages depends upon the number of segments your wall is being constructed, and this is something that you don't determine. This is limited by the fabricator if you are using a prefabricated component to quickly construct your wall. If it is a poured construction or cast in place, then you can definitely control what segment heights you would like to choose. Now after doing all this hard work, you would definitely like to see how it will affect your outcome or the results. So for this, I have recorded the animation of the results under the construction staging. So here you can see, first we dig out the foundation pit, then we place the foundation, then we place the block, the backfill, the reinforcement, and then we are continuing the construction in the same process, and you can see the deformation values changing in this legend here, and you can see the maximum deformation is occurring in these layers right here, and when the construction proceeds, you can see the zone is getting bigger and bigger. Now if it would have been a static analysis, you would have assumed that maximum deformation would occur somewhere in the lower layers, but in reality, the maximum deformation or most instability is occurring in this particular region. So this is where you will have higher stresses in your reinforcement members. This is where you will expect more stresses in the or less stresses in the wall in the soil layers, because they can be mobilized here. Also notice the contours of the deformation layers between soil and wall. So you can see that there is a dip in the soil where it is connected to the wall, and it is not kind of straight connection. So this also shows a relative displacement between the wall and between the wall and the soil, and this relative displacement is what is known as soil structure interaction. That is what I'm going to cover in the following slide. So I hope you were able to understand and appreciate the advantage of numerical analysis and construction stages for designing the retaining wall. Now here we'll take up soil structure interaction in more detail. So essentially it is nothing but a very simple stable system where you have one wall member, and this is the soil layer, and this vertical arrow is the surcharge, which may or may not be there, and this horizontal driving force, which is always there irrespective of the surcharge. This could be due to the unstable slope and the sliding wedge, or this could be due to the active earth pressure. So when these forces are acting onto the structure and you are modeling this behavior without considering any interface or without considering soil structure interaction, this is what you will observe. If your active pressure is high or driving forces are high, then you would see that the wall would deform something like this and the soil will follow it. So this is how it will look like if you don't consider the soil structure interaction or interface members. This is one possibility. Now let's say if the surcharge is very high, then the other possibility would be something like this. Again, the nodes are the wall members and the soil members are connected to the same nodes, so therefore you are seeing that they are being mobilized together. But what happens in real scenario? It's not this, it's not the second option, it is the third option. When whatever is the surcharge or the driving force, with the wall would deform something like this and the soil layer would not follow the top point or the topmost level of the wall. Rather, it would, based on the cohesion, would slip down, and this is what you would actually see. So we need to have something to simulate this kind of behavior in numerical analysis. Otherwise, we'll be ending up with incorrect models like A and B. So let's see what can we do to have this soil structure interaction going. So what we have to do is to apply a separate layer of elements called interface elements right at the surface of the wall which is facing the soil. And this interface element has various types of input values where you have to enter the normal stiffness modulus, which would be actually perpendicular to the wall surface and directly resisting the responding to the driving forces, and then shear modulus, shear stiffness modulus, which would be basically responding to the vertical or the surcharge forces. Then cohesion, that will determine the relative slipping, and the internal angle of friction. So as you can see here, whichever program or software you're using must have something to accommodate the interface properties, and these properties are generally determined through field test data. But if you're dealing with a complex soil type, which requires something like clay or unconsolidated soil strata, so what you have to do is you have to perform some detailed field test and determine other parameters as well. But one thing is sure or confirmed is that these values are obtained directly from based on the field test, and you have to perform different field tests depending upon the backfill material. I hope this explains the soil structure interaction and the role of interface elements in determining this soil structure interaction. Now, why this soil structure interaction is important? First, it determines the relative displacement, and secondly, it helps you to understand as what would be the behavior of the wall members when the soil mass is deforming and settling down, and therefore with the combination of these two, you can obtain optimal design forces for your structural components. So this brings us to the end of chapter 3, and here we'll be quickly going over what all we learned. So first of all, there are thumb rules based on field test and numerical models exist to assume the extent of soil strata around the structure to dissipate the stresses. Then backfill material and existing soil behave differently. Therefore, constitutive models with apt parameters should be used. The structural members like wall and with its foundation and reinforcement are considered to be within their elastic stress limits. The construction stage analysis is needed for segmentally constructed walls to determine the deformation and stresses in soil, wall, and reinforcement. And the interface elements in numerical models enable true soil structure interaction to consider relative deformation. And relative deformation between soil and wall gives accurate assessment of design forces for wall and reinforcement. And finally, interface properties are dependent on soil type, and inputs can be obtained from the field test. So now it's time for quiz number 3. 3 questions and 5 minutes duration. Alright, so everyone has submitted the quiz, so let's move on to chapter 4. So in this chapter we'll discuss the case study where 2D and 3D analysis was required for a reinforced retaining wall for the same project. So this is a project site. The client hasn't given us the permission to share the project name or the engineer who are working on the site on this project. So, but they have accepted the request of sharing the general outlines of the project so that engineers can benefit from them. And this is an ongoing project, so it is more sensitive. But nevertheless, because this project is a unique project in itself, and I'm sure very frequently most of the audience here would be getting involved in projects which are similar to this type, we realized that it would be worth while to share this project with you. So this is an excavation site, and as you can see, it is circular retaining wall that is applied all around it. They had to determine two main things. First, they have to assess the behavior of the soil structure interaction, that is the relative displacement that is occurring between the wall members and the soil. For this, they have to do a 3D analysis, and then they have to check the results that they are obtaining from the retaining wall and compare it with the field monitoring data. So why they need 3D and 2D analysis models? So as I mentioned in the very beginning, that sometimes your reinforcement layout varies along the length, or if your section is varying along the length, then you need to move one step ahead in 2D analysis, which is 3D analysis. And as you can see, this is not a regular structure, it is changing, it's a continuous structure. So then they have to consider the stresses that would be occurring in the wall members along this this arc line. So they have to they had no options but to have a 3D analysis model. Had this been a relatively straighter wall, then 2D analysis would have been sufficient, and this enabled them to obtain the relative displacement of the soil strata along the periphery of the wall. But still they had to do a 2D analysis. Now why? The 2D analysis gave them a better understanding of the actual forces that are occurring in the members. So they were able to see the interaction through the interface members and the actual forces that are developed in the reinforcement members here. So if we look at the results, so from 3D analysis, like I said, they took the displacement results and they used geogrids in this as a reinforcement material here. So they were able to extract the relative displacement. This is just the soil strata, this is just the wall members, and what are the relative displacements that are occurring or expected, because there was excavation going on this side, and they cannot afford for this wall member to fail and cause serious accidents. So they have to take precautionary measures accordingly by strengthening the wall members and extending the geogrids deeper. Then from the 2D analysis, they were able to investigate that where exactly or to what length they should apply these reinforcement members, and they were able to see the forces that are developing, and they were in line with what they were expecting. Also, they were able to capture the lateral deformation more clearly. Like I said, there was construction going on this side, where these were the retaining walls here. So just to be more clear on the point that there is the out of plane deformation of the wall is controlled, they check this model for the for 2D analysis and for lateral deflection. So then they took these two sets of results and they compared with the field monitoring data. So I'll directly share with you the conclusions of the finding. So the analysis results were compared with the field monitoring data. So first, the lateral displacement was matched with the first day's monitoring data, and this value was around 1.77 inch. Then it was monitored that additional lateral displacement around 1.2 inches occurred after 90 days, and this was due to the foundation material was not concrete but aggregates. Now it is quite obvious, it's not very hard to see or understand that if your foundation is not concrete and not monolithic with your wall member, then it is highly likely to have an additional lateral displacement as the soil stabilizes or the stresses are relieved or the soil is consolidated, and that's why we were having higher member forces in the lower reinforcements. So they were able to uh, uh, create the model and monitor the long-term effects of this analysis and how the wall would deform and match the results. So the settlement results became very important, and they had to first monitor the settlement that is going on in the field and compare it with what they were getting from the model file, and they were able to get the perfect match for the first day monitoring data. So like I said, in order to catch the long-term effects of the retaining wall, it was needed to do advanced numerical analysis such as fully coupled analysis. So that led to an advanced set of analysis that needs to be performed, which is not commonly done when you are dealing with very conventional, simple, straightforward retaining walls. But here, since it was a massive retaining wall, it was a huge construction and it was a very critical project because the excavation was going on, so they were actually lowering the strength of or the forces on one side. So they had to control the lateral effects, and since the construction would take longer time, they would like to monitor as how much deformation would occur in long run. So I'm not sure what drainage facilities were available on that site, so I cannot comment to what extent would coupled analysis be needed or would be helpful, but definitely we can say that the strata was clay, and no matter what happens, how good the drainage condition is, you would definitely have some built up pore water pressure that will take some time to dissipate. And if you were in the previous session, then you would be able to appreciate that for these kinds of slope stability and retaining wall design, you have to consider the fully coupled analysis, which is consolidation as well as slope stability. So these checks were performed, and if you're just curious what software was used, so they used Midas GTS for this project, and this project was turned in by one of our clients. So this wraps up what we would would be sharing today with you. I hope you enjoyed the session. We'll be looking forward to your feedback on this session. If you have any questions, comments, do feel free to write to us or directly give me a call, and we'll be more than happy to address them. And before I sign off, I'd like to share with you our next session, which is happening on October 2nd, 2013 at 3 p.m. Eastern Daylight Time. We'll be talking about applications of numerical analysis for dam stability. So do join us then. Thanks a lot for coming in today. Once again, this is Arun Sharma signing off from Midas Soft. Thank you. Bye-bye.